So with that background, we can get started with our course. Electrical circuits are interconnections of electrical components, and they manipulate voltages and currents in some way. Okay? Now, I think all of you have heard of voltages and currents. I would like some responses from the participants. What is a voltage? Perhaps you can type it into the chat window. Okay, I've got a number of responses here. Got a number of responses, and basically they kind of fall into two classes. You say that either the voltage is a potential difference or it's related to some force that causes current or that causes electrons to flow. Okay. Now both of these are of course quite correct, and I'll elaborate on these things. And similarly, I would like some responses on what is a current, what's an electrical current. Okay, again I've got a number of responses which say that a current is basically flow of charges. Okay, and some of you say electrons, which is quite correct, of course. Okay, and some of you also said that it is the rate of change of charges or rate of flow of charges, and these things are quite correct. Okay. And in the definition for voltage, some of you also related it to the electric field, which is quite correct as well. Okay. Now, I think all of you know that all of you have at least heard of Maxwell's equations, which relate electric fields and magnetic fields and charges. Okay. So you have charges that can create electric fields, and charges can move under the influence of electric field, they can move under the influence of a magnetic field, and so on. Okay. Now, of course, those are the basic equations which govern everything in electromagnetics, including our circuits. Okay. If you also recall from electromagnetics, usually it is quite difficult to solve the problems. Usually you end up having to do a lot of mathematics. But in circuits, things are a lot simpler. The reason I'll explain shortly. Okay, we are also dealing with electric fields and magnetic fields and flow of charges under the influence of either the electric field or the magnetic field. But there are some conditions that make our life a lot simpler. We can do things a lot more easily. and our primary variables will be voltages and currents, and these will be related to the fields. Okay, but what we usually deal with are not the electric field or the magnetic field, but voltages and currents. Okay. Now first let me take an electric current, and electric current, usually denoted by I, is the rate of flow of charge across some surface. Okay. So you could have some surface. I'm showing some pipe-like thing, and you could have charges flowing this way, and the rate of change of charge across the surface is the electric current through that surface. Okay. Now a couple of things. I think all of you know that it is electrons that do the flowing. It's the electrons that flow, and electrons are negative charge. So what we are looking at, what is defined as the electric current, is the flow of positive charges. Okay, it's really the negative of the flow of electrons. Now, as far as we are concerned, it is perfectly all right to think of positive charges are flowing, although it is electrons that are flowing, and the direction of flow of positive charges will be exactly opposite to the direction of flow of electrons, which are really the things that are flowing. Okay, it's okay for our purposes to think of currents as a rate of flow of positive charges through some surface. Okay, and also generally a very useful analogy for electric current is fluid flow. Okay, so instead of charges that are flowing, you can think of fluids that are flowing in pipes and so on. And for a number of cases which involve general rules about currents, this fluid flow analogy works quite well. Okay. Now, in our particular case, we will not be looking at charges flowing in arbitrary surfaces. We will be looking at currents that are confined to a wire. And a wire is a very good conductor. In fact, we will think of them as ideal conductors, which offer no resistance at all to the flow of current. So, we will be looking at currents that are confined to wires. Now, this is one of the aspects that make our analysis quite simple. Okay. Now, if you have charges in field somewhere, it's not very easy to calculate the effect of fields on charges, exactly how they move and so on. But we'll be looking only at electric currents in a wire or through some elements. So our job is a lot simpler. Okay. So you may have some wire like that, and you could have a current flowing from A to B. Okay. Now, as I said many times, this really consists of electrons flowing from B to A, but we can think of it as positive charges flowing from A to B. Okay, if the current is in this direction. Okay. We also don't worry about exactly how the charges are distributed across the surface of the wire. We will be only concerned with the total current flowing through the wire. Okay. And I think many of you know this already. The electric current has units of ampere. Okay, and this corresponds to carrying a charge of 1 coulomb in 1 second. Okay, so if 1 coulomb of positive charge flows from A to B in 1 second, that constitutes a current of 1 ampere from A to B. Okay. So here I have shown a wire from A to B, and I draw an arrow from A towards B, and I have marked 1 ampere, and that's what this means. Okay, 1 coulomb of positive charge flowing this way. Now I could also show the exact same situation. Okay.
So what's the chat? They're usually being very good about that.
Yeah, but I didn't get anything exposed
Sorry,
here.
so over here on full screen, is it? Okay. So we'll come
No,
on
no,
live.
it's not.
No problem.
No, I mean I was saying other things, but
Yeah, it's okay. Okay.
okay.